Hello. Today I'll be showing how we can include temperature and magnesium in our DNA simulation. Since we're going to have some magnesiums, they will be free floating and we'll have to have some sort of container to keep them close to our DNA. So these sprites, static sprites, are going to form our container. Let's name them borders and put them in a new game object. Next, we're going to be creating our magnesium ions. So this can be our magnesium ions, and they're going to have a collider and a rigid body. And make sure the gravity scale is 0. We're going to be adding some layers, border nucleotide and cations, so that we can control the collisions if we want to. And we're going to have a new folder, ion prefabs, so we can put our ion prefabs here. And a new script, ion controller or cation controller. And we're going to be including some force functions. So first one is we're going to be applying traction between the ions and the phosphates, cations and the phosphates, and repulsion between the cations. Yeah, naming cation would be better. I mean, it doesn't mean it won't work for ions too. And rigid body again, so we can refer later. So we're going to create defining the vector between the nucleotide and the ion, and then we're going to apply a force that will attract them to each other. Again, it's we're going to multiply with the attraction factor and the time delta, divided by the square magnitude of the distance. I'm going to apply the same thing to the nucleotide. So we're going to be applying this force both the nucleotide and the magnesium. And we're going to be applying the force that will repulse or push other cations away from each other. That is only we have to make sure that this is not itself. Again, normalized times a repulsion factor that we will define times the delta time divided by the square of the length or distance. And so we're going to be doing it every update. We're going to find all the nucleotide controllers and apply force, attraction force, and we're going to find all the magnesium ions or cations and apply repulsion. I'm going to make the mass smaller, and if you give some attraction and repulsion, it will start moving. Let's make sure that attraction is positive and repulsion is negative. Yep. And let's make copies. Now at the moment they're close clumped together, but once we give them some repulsion, cation repulsion, they will separate. Even though the phosphates are attracting them, they will be repelled at the same time by other cations attached to DNA already. And this is kind of an effect we expect to see. It's not allowing any more magnesium ions between the two nucleotides. Now let's create a copy count so the magnesium ion can copy itself. So depending on the number we enter, so we don't have to create at the beginning, we can just change the number and then we'll have that right number of magnesium ions. We'll need the border, so I think about 12 will be suitable for the maximum and minimum limits for creating magnesiums. And the quaternion of identity. And once we increase the copy number 20, yep, there we go. Now we can apply the heat effect, which is basically going to vibrate all the particles, nucleotides, and the cations alike. I'm going to have a random vector, and that random vector multiplied by the temperature, and the delta time is going to give us how much this is going to move. We're going to apply the same thing to the nucleotide controller. So again, we need an apply heat function and call it every update. Also magnesiums, yep. Actually, yeah. So we're going to have we can have a simulation manager, so we can control all the temperature in one place and other factors as well instead of separately. So static temperature, range between 0 and 500. Can have electrostatic force multiplier. Not sure if we're going to use that one. And the hydrogen bond force multiplier, which we already have. I'm going to change that one. Move to here. Instead of calling them static, we can have a singleton main for the simulation manager. So we can use control the temperature in there. So we're going to remove these and then place simulation manager main. Yep, static main dot hydrogen bond force supply. And take the temperatures. We don't need these anymore. Can put all the temperature into simulation manager. So we need to change the cations. Yep. We don't need this at the moment. And there we go. We have temperature and the hydrogen bond multiplier. So we can, yeah, let's increase, put some more strands. Let's also put these factors or variables into the simulations manager too. Just keep everything nice and tidy. They need to be public though. Yeah. Can play around with these parameters. Now it's all clumped together because the cation repulsion was positive. Now once it's negative, they fly apart. Let's change these sequences with something that will form double-stranded DNA and see how is it going to change. Okay, two positive strand, two negative strand. And let's set up the parameters as we have found before that are suitable. No, negative. And we can start watching. They should eventually find each other and start forming double-stranded DNA. In the next episode, we'll be looking into drawing real-time diagrams for indicating the number of hydrogen bonding to help us see the DNA formation. And thank you for listening, and please comment below.